Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is lecture video 30 and lecture 15, part A. We're going to introduce confidence intervals for the mean. And so let's get started. So we're going to use a random sample in this course. So that means that x sub I are IID. That's independent and identically distributed. So they have the same mean and the same variance and the same population or distribution. Okay? And our goal is to construct a confidence interval or CI for mu. So we'll come back to that. I want to talk about some basics here so that this is a lot clearer than maybe the book presents, so that you have a little more information here. Okay, so let's say that we want a 95% confidence interval. Okay, what is this going to look like? Well, the first thing that we need to know is we need to know that this is we're going to call it C. It's the confidence level. So we're going to have a lot of things that have the word confidence in there. So in order to have a confidence interval, we need a confidence level. How confident do we want to be? Okay? And then we're going to have an interval. So what we're going to do is we're going to set this up so that if we're talking about z here, the standard normal, then when we look at z, we're going to say that the confidence level is going to be 1 minus alpha. And then, so this is going to be something we call z naught, or negative z naught here and z naught there. And this c is the probability that the interval, that the CI, which is an interval or range of values, actually contains or covers the population parameter. In this case, it's mu. Okay? So C is a probability. And alpha is the type 1 error of a test. And in this case, it's called the significance level. And this is, for this case, the probability that the confidence interval does not contain mu. Now, we are going to use something called the frequentist method or point of view. And this says, that mu is an unknown constant. So no probability is associated with mu because it's a constant. There's just no probability about mu. Mu is some one value. It doesn't change. At least it's constant at this point. And we don't know it, and we want to estimate it. And so we will use, then the Bayesian point of view is that mu is a random constant, is a random quantity or random variable. So it changes maybe over time. that has a distribution that may be different than the distribution of x of xi. Okay? So we are not going to use this point of view in this course. I want you to know about this point of view because there's still some Bayesian statisticians out there, and I am neither a frequentist nor am I a Bayesian. I see the value of both of them depending on the situation, how you're viewing the problem, and which point of view seems the most reasonable in that situation. That's the method that I'm going to use. We are not going to discuss a Bayesian, we are not going to use the Bayesian point of view, so I shouldn't circle it. We are going to use the frequentist point of view in this book. We use this. And so the idea is that mu is here, and we're going to calculate a confidence interval, and it might look like this. And another confidence interval might look like this. And then another confidence interval might look like this. And another, well, we should make them the same length here. So let's see. That's about right. And then another confidence interval might be down here, and pretend they're all the same length. Another confidence interval might be way up here, and you'll notice that some of these confidence intervals contain mu and some do not. Most will. Okay? And mu will not necessarily be in the middle of the confidence interval. It's just somewhere inside the confidence interval, we hope, but not all the time. Okay? So if we calculate, or if we, okay, let me be more specific about that. If we take a random sample of size n, whatever that size is, but if we take 1,000 random samples of size n that are independent of each other, okay? So we do truly random, and we make sure that we're not doing something to repeat values, and so we have to have a large enough sample size so that we don't have a high probability of selecting the same observations in multiple of these confidence intervals, okay? So if we have different observations in all of the confidence intervals, then we're going to have independence. So let's say we take 1,000 random samples. I'm going to make that a little clearer. 1,000 random samples of size n. And we calculate a C% confidence interval for each sample. All 1,000 CIs will be different if it's from a continuous distribution. Okay? And by the way, we are in this section continuous distributions. Okay? We can talk about discrete distributions, but it depends on the sample size as to whether we're going to say that discrete distribution can be approximated by a normal distribution, in which case we have a continuous distribution. Okay, so we take 1,000 random samples and we calculate a C% confidence interval for each sample. Then all 1,000 confidence intervals will be different, and we expect, so I'm going to say this differently, a little little more technically. So the expected number of confidence intervals that contain, so this is expectation, so a mean is what we're saying. The expected number of confidence intervals that contain mu is C times 1,000. Okay? And the expected number of CIs that do not contain mu is 1 minus C times 1,000. So let's do an example here. Let's say that let's say that C is equal to 95%, which is 0.95. Then 0.95 times 1,000 equals 950 confidence intervals that CIs that are expected to contain mu. Somewhere in there, this CI covers, if we look at it like this one covers this region, this 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 one covers this region, this one covers this region, this one covers this region. And so the probability that the CI covers mu is C, which is in this case 95%. So we expect 950 of these confidence intervals out of 1,000 to contain mu, and 1 minus C times 1,000, which is equal to 0.05 times 1,000, which is equal to 50, are not expected to contain mu. So when we calculate a confidence interval, we have no idea if mu is actually in there, but we are 98% confident that the interval contains mu. Now mu is staying the same, it's constant here. What is changing are the CIs. Let's say CI1, CI2, CI3, CI4, CI5, CI6, CI7. I hope you get the idea. Okay? The random quantity is the interval, not mu. The random variable is the confidence interval, not mu. So when we talk about the probability, when we interpret a confidence interval, we are going to talk about the probability that the interval contains mu, not that mu is in the interval, because that implies that mu has some probability, and it does not. Okay? So, now, you might ask, why are we using an interval? We already know x bar. So x bar is the best point estimate for mu. We proved this in an 800 level course. We proved that the MSE, the mean square error of x bar, is equal to the lower limit of MSE possible. Okay? And so the MSE which is equal to the bias of x bar squared plus the variance of x bar. And x bar is unbiased, so this is 0. The expected value of x bar is mu. So this is equal to the variance of x bar. And so the variance of x bar is the lowest variance for a point estimate that you can get. So it is the best point estimate. And we know that for n greater than or equal to 30, or by the CLT, x bar is approximately normally distributed with mean mu and variance sigma squared over n. So it has some probability. So what's the probability that x bar is equal to mu? It's a continuous distribution, the normal distribution, so this is exactly 0. That's why we use an interval, so that we can have some probability, that we can have some confidence that mu is in or near that interval. X bar, we know it's the best point estimate, but, and it's unbiased, but the probability that x bar is equal to mu is still 0. There is no probability there. So the only way we can get probability is to create a range of values around x bar, our best point estimate. Use that best point estimate to calculate a interval, a confidence interval. So the confidence is a probability, like I said. So we have some probability, a high level of probability that the interval actually contains the parameter we're looking for. The confidence level that of x bar being equal to mu is 0. So we don't want that. We want something better. And so that's the whole idea of this chapter 7 that we're going to cover, is creating confidence intervals about a parameter so that we have some probability, some confidence that the interval contains mu. The wider the interval, the less precise it is, the less information we have about mu, because the bigger the values that it could be. The smaller the confidence interval, the more precise that confidence interval is, then the more information we have concerning x bar and the distribution it comes from. So, and in graduate level courses, you'll learn about the information. I don't want to be too technical. You'll learn about the concept of information and how it relates to all of this, okay? So the more information, the better the information, the more precise the interval, the shorter the interval. So, and that information concept will determine, which variable is the best point estimator if we can find such. Okay, so, all right. So I hope that has helped you understand, one, what is a confidence interval, and two, the idea of it, and why. Two is, why are we doing an interval instead of using a point estimate? Why are we going that next step? And so I hope that explains it. We are going to look at 4 cases for a CI for mu. The first 2 cases, we're going to say that sigma is known. This is an unlikely event in real life, but it does happen occasionally. And then when sigma is known, we have 2 different situations. We have a small n is less than 30, and we have a large n is greater than or equal to 30. So the CLT applies here. Here, we're going to see that we have to have, we can only use these methods if x of I is normally distributed, has a normal distribution. So here's the first theorem, and it's talking about the linear functions of independent normal random variables. x1 to xn are going to be independent random variables from some normal distribution. They could be from different normal distributions in this case, so more general. They do not have to be identically distributed. We have mu sub I, so x1 could have a different mean than x2 or x3, etc. And sigma sub I squared, so again, the variance could be different. And what it says is a linear combination of these random variables, so a1 is a constant times x1, and these constants can be positive or negative. So this can be plus or minus, either way, depending on the constant. So a1 times x1 plus a2 times x2 plus ... an times xn. That is a linear function of the x1 up to xn random variables. So y also has a normal distribution. If every one of the random variables has a normal distribution, then any linear combination of them also has a normal distribution. That's a powerful theorem to know. Now, let's talk about the sample means, x bar. Well, so if x bar is from a random sample of size n, from some distribution with mean mu and a variance sigma squared, then we can see that x bar is equal to, we know from the definition, is x1 plus x2 up to xn divided by n, the number of random variables. And this can be rewritten. We can pull the 1 over n out front and then distribute it. And we have 1 over n x1 plus 1 over n x2 plus up to 1 over n times x sub n. And this is a linear function of random variables. So if all x sub I are normally distributed, let's say mu sub I sigma I squared, if I don't have to say all, implied by the I, then y equals x bar is normally distributed. I'll call it mu star sigma star squared. Okay? So it also has a normal distribution. So that's very handy. If we start with normal random variables, then the mean is normally distributed regardless of how many random variables there are. If it's 2, then it's still normal. If it's 100, it's still normally distributed. So this is where the case for n is less than 30, then we need to have the original data normally distributed in order to be able to use the formulas we're going to derive in the next video. All right, so that is it for this video. So I hope that's been a good introduction to confidence intervals for you. If you have questions, come to virtual office hours. If you need help before you can make it to virtual office hours, email me. But please email me a copy of the picture of the problem, because I may not have it available, and a picture of your work so far so that I can get back to you and help you faster and better. Please take care of yourself and stay safe, because we want to see you here next time.